Once again, I welcome you to my online classes. As I discussed in the previous video, we are discussed regarding electrically conducting fluids and electrically non-conducting fluids, and they are also called as ordinary fluids. And so, in the previous class, we discussed that incompressible electrically conducting fluid, or it may be ordinary fluid, they are practically liquids, whereas compressible deals with gaseous form. Okay. So, and the density varies with respect to pressure as well as temperature, right? In electrically conducting fluids, there will be two types of volume forces. There will be two types of volume forces. So, in electrically conducting fluids. In electrically conducting fluids, there will be two kinds of volume forces. One is volume force due to gravity, that is so called body force. Okay, due to gravity, that is so called body force. And other one is volume force due to electromagnetic fields, and that force is known as Lorentz force. Okay, and that force is known as Lorentz force. One is volume force due to gravity, that is so called as body force, and volume force due to electromagnetic fields, that is so called Lorentz force. There will be two kinds of volume forces in electrically conducting fluids. Here, electrically conducting fluid depends on the value of the sigma. So what is sigma? Sigma is nothing but electrically conductivity parameter. What is this? Electrically conductivity parameter. Electrically conductivity parameter, right? So sigma is known as electrically conductivity parameter. So here, electrically conducting fluids depends on the value of the sigma. Means whether sigma is less than 1 or sigma is equivalent to 1 or sigma is greater than 1. Means sigma is so small, sigma is average, sigma is highest. Higher values of electrically conducting parameter. You can find electrically conducting fluids, case 1. Okay. Case 1 deals with, you can find electrically conducting fluids in which sigma is very small. You can find electrically conducting fluid. In this case, the sigma is so very small. So, and they are called as poorly conducting fluids. They are called as poorly conducting fluids. If sigma is very small, then the electrically conducting fluids are called as poorly conducting fluids. Okay. And the characteristics of poorly conducting fluid is the electric field is conservative, means constant, conservative. Okay. So in electrically conducting fluid, if sigma is very much smaller than 1, then they are called as poorly conducting fluids. And the characteristics of poorly conducting fluid is E is conservative. E is conservative means it doesn't varies. Okay, it does not varies. It is not possible to get more electricity like that. Okay, it is conservative. And case 2 deals with the fluid, electrically conducting fluid, in which sigma is equivalent to order of 1, means average. So average. So then there are electrically conducting fluids in which sigma is order of 1, and they are called as finitely conducting fluid. Finitely conducting fluids. Okay, finitely conducting fluids. If sigma is order of 1, then they are called as finitely conducting fluids. If sigma is very much lesser than 1, then they are called as poorly conducting fluid. The characteristics is E is conservative. Here the characteristics is the finitely conducting fluid, the electric field is non-conservative. The electric field E is non-conservative. In this case, E is conservative. Here E is non-conservative. In poorly conducting fluids, E is conservative. In finitely conducting fluids, E is non-conservative. Now come to case 3. In case 3, the remaining is sigma is very much lesser than 1. Very much greater than 1. Then they are called as, okay, so less than already over, equivalent to 1 over. Now it is pretty much greater than 1. It is pretty much greater than 1. Then they are called as perfectly conducting fluid. Perfectly conducting fluids. Okay, perfectly conducting fluids, right? If sigma is pretty much greater than 1, then they are called as perfectly conducting fluids, right? The characteristics is, here the total EMF, namely, right? Due to conduction means E, EMF due to conduction, and conduction current means J is equal to sigma into E, right? This is conduction current. This is so due to conduction, right? So this and this, EMF due to this and EMF due to this has to be zero. There will be no wastage of current. There will be no electric field. So there will be no wastage of, there will be no electric field lines on the electric wire. So that is, they are called as perfectly conducting fluids. So one is poorly conducting fluid, other one is finitely conducting fluid, and other one is perfectly conducting fluid. In poorly conducting fluid, E is conservative. In finitely conducting fluid, E is non-conservative. And in perfectly conducting fluid, the total EMF, namely EMF due to conduction, and so the induced EMF due to conduction and induced EMF has to be zero. EMF due to conduction and induced EMF has to be zero. Okay. Now, so we can study what is Mhd. Right? Mhd is the study of electrically conducting liquid under the influence of electromagnetic field. There in mechanics we have studied only the pressure difference, temperature difference and those things. In Mhd along with them, so we have to study the liquids, means hydro means liquid, right? So we have to study, electrically conducting liquids, especially non-conducting, there will be no use of Mhd. The liquid must be conducting. It is the study of electrically conducting liquids under the influence of electromagnetic fields. That is so called Mhd. In other way, we can define Mhd as the study of interaction between electrically conducting fluids and electromagnetic fields. Okay, electrically conducting fluids and electromagnetic fields. Interaction between electrically conducting fluids and electromagnetic fields. This interaction based on, this interaction means interaction between electrically conducting fluid and the electromagnetic fields. This interaction so is based on two principles and they are called as basic principles of Mhd. Okay, this interaction is so purely based on two principles. They are called as basic principles. Okay, basic principles of Mhd. First principle is principle of motor. Right? Principle of motor is one of, first principle of Mhd, or you can say it as second also, no problem. But there will be two principles. One is principle of motor and other one is principle of generator. So first we have to know about what is, the meaning of principle of motor. I think you know motors. So electric motors, you can use them for, pumping the water from the sump and pumping the water from the bore wells, pumping the water from open wells and grinder even in mixture, okay, in fans, they are all motors, they are all called as motors. So on what, mechanism it runs, so that is so called as principle of motor. So what is the principle of motor? A conductor carrying the current J, a conductor carrying the current J across a magnetic field, B, produces the force that is so called J cross V, okay, produces the force called J cross V, that is so called Lorentz force or Lorentz, Lorentz force or Ponder motive force, Ponder, Ponder motive force, right? So you can call this as, a conductor carrying a current, carrying a current across the magnetic field. A conductor carrying a current across the magnetic field produces the force that is so called J cross B, and it is known as Lorentz force or Ponder motive force, and this is known as principle of motor. Now, so second principle is called as principle of generator, okay, generator. So principle of generator, here the reverse process. So motor using the current it runs. Principle of generator is, if it runs then we can find, it produces the current, that is principle of generator. So here a conductor moving with the velocity q, across the magnetic field B, a conductor moving with the velocity q across the magnetic field B produces the current that is given by J is equal to sigma into Q cross B, okay, J is equal to sigma into Q cross B, known as induced current, okay. So here if we give the current to the instrument, it will runs, motor uses the current to run, but in generator if it runs then it produces the current. Here a conductor carrying a current J across the magnetic field B produces the force called Lorentz force or Ponder motive force. So the principle of generator is, a conductor moving with the velocity q across the magnetic field B produces the current that is so called J is equal to sigma into Q cross B, and it is known as induced current, okay. So these two are, or it may also known as induced EMF, okay, induced EMF. Look here, if Q is 0 means if velocity is 0, then obviously J becomes 0. Means if it does not runs, then there will be no current. If it does not runs, there will be some sort of velocity. As it increases, so your electricity produces becomes more, right? So these two are called as principles of magnetohydrodynamics. But to understand MHD, magnetohydrodynamics, first we have to study electromagnetic fields, okay, and the fluid flow. So if you studied both of these, then you can understand MHD, otherwise it is not possible to understand MHD. That's why to understand MHD, first we have to study, so what are the electromagnetic fields, and so what do you mean by fluid flow? First you have to study, so electromagnetic fields, okay. So first you have to study electromagnetic fields. To study electromagnetic field, you have to study electromagnetic theory, right? So first you have to study electromagnetic theory to understand electromagnetic field, to study MHD, okay. This is the reverse process. To understand MHD, you need electromagnetic fields and as well as fluid flow, okay, but so to study electromagnetic fields, you have to study electromagnetic theory. Now To study electromagnetic theory, there will be two approaches. To study electromagnetic theory, there are two approaches. So one approach is known as field approach. Okay, one of the approach is known as field approach. So this, field, F-I-E-L, field approach. Okay, so to study electromagnetic theory, there will be two approaches. The first approach is called as field approach, and it includes 5 fields and one scalar. Okay, one scalar, right? So this field approach includes 5 fields and one scalar, right? What are those 5 fields? First one is known as D, dielectric field, okay, or displacement vector. It also called as displacement vector, okay, displacement vector. This is a vector quantity D. It is known as dielectric field. Another one is E. This is known as electric field. Right? Electric field, and this is also a vector. And then B, magnetic field intensity. Magnetic field, F-I-E-L, field intensity, right? So B is known as magnetic field intensity. And then H is known as, so the B is magnetic induction, not magnetic field intensity, magnetic induction, sorry. This is B is known as magnetic induction, but H is known as magnetic field intensity, okay, magnetic field intensity. D is dielectric field, E is electric field, B is magnetic induction, and H is magnetic field intensity, right? So and then J is current density. Vector J is current density. So these are the 5 fields, okay, and J is current density. One scalar is nothing but rho E. This is nothing but density of distribution of charges, right? Rho E is nothing but density of distribution of charges. So 5 fields and one scalar. These are the 5 fields: D, E, B, H and J. Dielectric field, E is electric field, and B is magnetic induction, H is magnetic field intensity, and J is current density, and one scalar is rho E, that is nothing but density of the distribution of charges. And these 5 fields and the scalar, okay, these 5 fields and the scalar are governed with some laws, some basic laws, and there are different laws like Gauss law, Faraday's law, okay, Ampere's law, and Solenoidal property. Let us see one by one. So these 5 fields and one scalar governed by following laws. First, as a first one, I am going to take Gauss law. What is Gauss law? I think you know me. I think you may know it in your PU level. So what is it? This law connected with electric flux and charges. What it says? It states that the flux is proportional to charges. It says that flux is proportional to charges. Okay. Flux is proportional to charges. This law is connected with the electric flux, and it is denoted by capital N. Okay. The electric flux N and the charges Q. Electric flux N and the charges Q. Flux is defined as, flux is equal to, it is denoted by capital N. So, okay, and is, flux of what? It is nothing but flux of the electric field E. Flux of E is nothing but, it is denoted by capital N, and it is defined by surface integral of E dot ds. Okay, because you can find the charges only on the surface, right? Surface integral of E dot ds. This is known as the flux. And as you know, this law states that electric flux is directly proportional to the charges, right? So that's why, therefore, the flux N is equal to some constant into Q, because N is proportional to Q, means flux is proportional to charges, where C naught is constant of proportionality. Therefore, this is equal to 1 by epsilon naught into volume integral of rho E into dV. That is number of charges, charge density, and C is known as constant of proportionality, and it depends upon the units what we choose, right? This is so called Gauss law. Now come to Faraday's law. Faraday's law, right? What it says, actually this law is connected with the rate of change of magnetic flux and electromagnetic force, whereas Gauss law connected with electric flux and charges, and Faraday's law connected with the rate of change of magnetic flux with electromagnetic forces, fields. It is given by, as you know, force is equal to line integral over the contour C E dot dl, because magnetic lines creates on the wire, okay, that's why. So line integral over the closed contour C of E dot dl, this is force, and as defined by flux of electric flux, the magnetic flux also defined, that is given by flux of M is equal to, right? So B, magnetic field B is equal to magnetic flux, okay, magnetic flux. This is equal to, and it is denoted by some phi, and is given by, as same in the electric flux, so surface integral of B dot ds. If it is electric flux, it is given by E dot ds, surface integral. If it is magnetic flux, then B dot ds, okay. So this is magnetic flux, so where S is stationary. Now the rate of change of magnetic flux means d phi by dt is equal to surface integral of del B by del T, right, dot ds. This is rate of change of magnetic flux, and this is equal to what? According to the law, it is equal to the magnetic force acting on it, right? The electromagnetic force acting on it. So that is given by, line integral over a closed contour C of E dot dl. Here I have taken negative sign. What is the reason of negative sign? The negative sign is due to Lenz's law, this is due to Lenz's law, okay, Lenz's law, Lenz's law, okay. The negative sign is due to Lenz's law, so I will define what is Lenz's law in the next slides, okay. Just now, so remember it, the negative sign is due to Lenz's law. It creates the opposing forces. That's why we have taken it as a negative sign, right? This is so called your Faraday's law. What is Faraday's law? The rate of change of magnetic flux is equal to the electromagnetic forces acting on it, right? Electromagnetic forces, and negative sign is due to Lenz's law. This is your Faraday's law. Now come to third one, that is Ampere's law. Ampere's law. What it says? It says that the circulation of magnetic field produces a current. The circulation of magnetic field produces a current. So mathematically it is defined as line integral over a closed curve C of H dot dl. You know the definition of circulation in fluid mechanics. So as same there you have studied that it is given by line integral over a closed curve C, okay, line integral over a closed curve C, Q dot dl. This is due to velocity, here due to magnetic field. That's why we have taken magnetic field intensity H, right? Circulation of magnetic field is I mean it gives rise current, I mean it produces current. I call it as IT. IT means total current, and it is nothing but surface integral of JT into ds. Okay, total current density. So JT means total current density means J plus JD. What is J? J is true current and JD means displacement current. So this is true current, okay, and this is displacement current. So and this displacement current arises only in dielectric materials, okay, only in dielectric materials, and this is known as your Ampere's law. And next one is solenoidal property. Solenoidal property. What is solenoidal property? Solenoidal property is nothing but, so just like continuity equation for the magnetic field. Continuity equation for the, velocity, it is given by, so q dot d, del dot q is equal to 0. As same in, so conservation of mass equation, the solenoidal property is given by del dot h is equal to 0. This is so called the solenoidal property. Okay. So by this I am going to conclude this video. In the next video I am going to take the second approach. These are concerned with the first approach, that is nothing but field approach. So in this approach you come across 5 fields E, D, okay, J, B and H. Okay. So electric field, current density, right? H magnetic field intensity, and B magnetic field and dielectric field, and one scalar, that is so called rho e, that is nothing but density of the charges, These 5 fields and this one scalar connected with these 4 laws. One is Gauss law, another one is Faraday's law, another one is Ampere's law, and one more is solenoidal property. Now I am concluding this session with these 4 laws, and next we have to pass on to the second approach. Let us see in the next video. Okay, thank you.